Swayam Prabha. Digital India. Educated India.
So, we will try to wrap up this problem of Taylor dispersion in a circular pipe today. Okay. And the idea is, this is the equation which we had derived in the last class, the dimensionless form of the equation, and this basically represents how the temperature changes with position and time. Okay. In a moving reference frame. So, Z tilde is with respect to the moving reference frame. I have not decided what the L characteristic is. So, I just left it as L here, but basically L characteristic will be much more than A. So, this term will be small. Okay. This term arises because of the conduction term. How did this term come? This represents the axial conduction. Okay. And I want you to remember that if you have only axial conduction, the A squared by L squared represents the intensity of axial conduction. Okay. I mean, in our equation we had the radial conduction, axial conduction, the convection, time derivative, change to moving reference frame, we got this, and this represents this. I will come to this towards the end. What I want to do is I use a slightly different notation, because last class I put some bar, tilde and all that is just confusing. So, I am going to write theta as theta A plus theta D, A for average, D for deviation from the average. Okay. So, theta A represents average and theta D represents this is the average, and this is the deviation from the average. Averages across the cross section. Okay. So, what I want to do is keep life simple a bit, and again I will just say that integral of theta d from 0 to 1 2 pi r dr is 0. Okay. Because if I integrate this equation with respect to 2 pi r dr, this will give me theta average, this will give me theta average, and therefore this has to be 0. So, basically we have some average, the distribution of all the other quantities will be 0. Okay. We will use this sometime. Now, I want to substitute this in this equation here. Okay. And to keep life simple, right now I am just going to neglect this term. I do not want to keep writing it again and again. So, I am going to neglect this last term and write Peclet number times A by L times d theta A by dt plus d theta d by dt plus 1 minus 2 r squared. Okay. You forget star all assume is all 2 r star squared, no, this should be squared, times d theta A by dz plus d theta A by d theta d by dz. It multiplies this equals 1 by r d by dr of r d by dr of theta a plus theta d. Okay. Theta a is average in the r direction. Therefore, this will be independent of r, okay, and this will be equal to 1 by r d by dr of r d theta d by dr. Okay, because this is independent of r, it is averaged over the cross section. Now, what I want to do is, I want to take the average of, I want to basically integrate this equation with respect to 2 pi r dr from 0 to 1. Okay. Average means I will again divide by 2 pi r dr. So, because it is there in all the terms, I do not worry about that division. Okay. So, integrate with respect to 2 pi r dr from 0 to 1. Okay. So, theta a does not change with respect to r because I have averaged it out. So, when I average this theta, so theta is independent of r, it depends only upon t and z. So, when I average this out, I will get d theta a by dt because it is uniform. So, I will get Peclet number into a by L times d theta a by dt, okay, when I am averaging it out. This is average of the deviation. So, deviation, remember, the average is 0, okay, and this has derivatives with respect to t and z, so I can pull it out and I am integrating in the r direction. So, this is the derivative of this will be 0, I mean the integral of this, the average of this will be 0. So, plus 0, okay, this gives me this gives me this term plus average of, so now I have d theta a by dz, this is independent of r, okay. If this is independent of r, so what is the average of this? This is the average of, this is the perturbation of u, we saw that in the last class, the average of this will be 0, you can integrate out and check it, okay. So, this term will give me 0, but this term is a u dash and this is the deviation u d and theta d. This will not be 0, so I have one term 0 to 1 minus 2 r squared times d theta d by dz into, what did I say, 2 pi r dr, no, 2 pi r dr is what I get. This term is the product of two disturbances. This is my ud, because when I write it for u, you get actual u is average u plus this. So, actual u is, what is actual u? 2u into 1 minus r squared is actual u. I am writing it as u plus u times 1 minus 2 r squared. So, this is my ud, this is u average, okay, all my u's are looking the same. So, this is ua. Okay. So, I am just writing it like this. So, because this is a product of two disturbances, this is not 0, and what do I get here? Right hand side is 1 by r d by dr of r d theta d by dr into 2 pi r dr from 0 to 1, and this will basically be r times d theta d by dr evaluated at r equal to 0 and r equal to 1, okay. When you integrate this out, because your r dr that cancels off with r dr, you get this. Now, when you evaluate it at 1, you will get d theta d by dr at the wall, and we said it is insulated. So, there is no flux. Okay. So, there is no flux for theta. Theta A is constant, so there is no flux for theta A, and because there is no flux for this, there has to be no flux for theta D. Okay. So, no flux boundary condition is on theta. This guy has no derivative, this also will have no derivative. So, that becomes 0, and at the other end r equal to 0 is 0. So, this is 0. Okay. So, what I am trying to get at is d theta A by dt is equal to the average of ud d theta d, oh no, yeah, theta A, no? Yeah, I just changed the notation, I am getting confused. So, I put this bar to signify average. That basically, this is 2 pi r dr, integral 2 pi r dr, okay, that is this term. So, that is 0, everything is 0. So, basically d theta A by d is equal to minus of this. So, we are saying that the way the material derivative for theta A, the average temperature changes, is decided by the average of this thing, okay, the average of the disturbance variables, the deviation variables. So, this is definitely not all that easy to solve, right, because on one side I have average, on the other side I have deviation. So, what we do is we write this thing as some constant times d square theta average by dz squared, and that is what we have to find out now. Okay. Because I said when this slug is moving, the distribution of the temperature is symmetric about the mean point, right. And when is it symmetric? When there is something like a conduction term present, because it will conduct in the front and it will conduct in the back. So, basically this is approximated or represented like this. How to do this we will see, but before that I want to tell you that there is a similar kind of a situation which prevails in turbulent flows. So, in turbulent flows, we have this concept of turbulent viscosity or eddy viscosity, and there again we take into account the okay, this is similar to the concept of Reynolds stress and turbulent viscosity in turbulent flows. There again you will do something very, very similar. You will write the in turbulent flows, remember the velocity, there will be mean value and there will be a fluctuation. Laminar, everything is steady, nothing is changing with respect to time. Okay. So, in turbulent flows what will we do? We will write u as u average plus ud, and the convective term is divergence of rho u, right. I am trying to think whether I want to erase, what I want to keep. I think I want to keep that. So, I am going to come here, okay. I want to use that equation again. So, in turbulent flows what we do is just to show you some analogy with what we have, divergence of rho u, this is your convective term, and remember this is also coming from the convective term, okay. So, I am saying if you write this divergence of rho ua plus ud and ua plus ud, the UD term will come, this one of these terms, there will be 4 terms here, one of these 4 terms is divergence of rho UD. UD is a deviation, and this is basically what is called my Reynolds stress term. The rho UU is my stress term, rho UD is the Reynolds stress, and the divergence of the stress, this we approximate as mu turbulent times d square u by dy squared. Okay. So, same thing we are doing here, this is the deviation, okay, ud, and in there you get dud by dz, here I am getting just ud and d theta d by dz, I am representing it as a conduction. The point I am trying to make here is that sometimes you can, when you are doing some work, there could be concepts from something else which you can use when you are for your research. Okay. I mean that is something which you have to understand, that when you are doing solving a problem of some kind, you can basically use some ideas, and the only way you can figure out these things is if you do a lot of reading, only if you read. And so when you do research, you should not confine yourself to necessarily reading exactly only about your problem, you should look at other things also you can read, okay, and it does not necessarily have to be only technical, it could be non-technical, it could be story books, it could be anything, and when you do that, you would possibly get some idea for solving your research problem. Okay. So, I am just trying to make the connection of this eddy viscosity and Reynolds stress that exists in turbulent flows to this dispersion problem, because there also the same divergence of this thing, we are doing the same thing. You know, you have u theta, okay. Just to tell you that you need to try to make these connections, and then your understanding of a problem becomes better. Okay. So, that is that. Now, what I want to do is I want to relate. So, our objective now is to try and represent this in terms of this deviation average in terms of the second derivative in theta a, so that it represents conduction, because that is what I am observing. How can I do that formally? I mean, I am going to do some you know, so I want to find out what is my equation for theta d. Okay. ud I already know, ud is 1 minus 2 r squared. This is known, I do not know theta d. So, I will come here and this is what I want to keep. Yeah, I will come to this equation on top. What is the equation? So, how to find theta d? In fact, I want to see if I can write theta d in terms of theta a, because that is what I want to do. I want to write this in terms of, because this I know as a function of r, I do not have a problem, it is 1 minus 2 r squared. This if I can write in terms of theta a, then I can try to get this, okay. That is the plan. So, now let us see what we can do. I definitely need to keep d theta a by dt, d theta a by dt is this quantity here, okay. So, I am going to write d theta d by dt plus, or rather minus. So, I am substituting for d theta a by dt, okay. And I am going to put this Peclet number into a by L, which I forgot. Then plus 1 minus 2 r squared d theta a by dz plus d theta d by dz equals 1 by r d by dr of r d theta d by dr. Okay. Basically, I have taken the same equation, I have kept the theta d term here, I kept this term as it is. For d theta a by dt, I substituted this. I already derived that. And so, I am going to write this in a different way. Equals this term I am going to take to the other side, okay. It becomes plus. Okay. So now I'm going to make, see, one thing is, one way you can do it is, you know, solve for, if you know theta d, you can substitute the value here and you can calculate this, okay. So to solve for theta d, I have to solve for this equation. This equation is the one which tells me how theta d actually changes with time and space. But if I am going to solve this equation, then I know theta d, I can directly use the theta d and find my theta, because theta is theta a plus theta d. So rather than do that, I am interested in how the average is changing, okay. So point is, I want to find out how theta average is changing. That depends upon this. If I know theta d by solving this equation, I can get theta a plus theta d, okay. But I mean, I don't want to do that. I want to see if I can get a shortcut, make some arguments, approximations, okay. So that's what we're going to do. So one, and this is where I think Taylor used his intuition or insight to make some approximations, which I will talk about now. So rather than find theta d by solving the equation for d theta d by dt, can we approximate it and find theta d as a function of theta a, because then the right hand side will have theta a and I can go on happily and do whatever I want, okay. That is the idea. So first thing what our man Taylor did was, he said, look, the deviations are going to be much smaller than the mean value, okay. So this is A, I think my A and D are looking the same, okay, this is A, this is D, okay. His point was theta d, so Taylor's intuitive approach. Now I must tell you that it is also possible to do this very formally. Whatever I am doing by making physical arguments, you can do it mathematically, okay, but there is some theory for that which I don't want to talk about, okay. So is theta d is much smaller than theta a, okay. If theta d is much smaller than theta a, on the left hand side I am going to neglect this theta d derivatives and only retain the theta A derivative. Then LHS is going to be Peclet number times A by L times 1 minus 2 r squared times d theta A by dz. Okay. I am only keeping this term. This is the approximation we are making. We are neglecting these two terms, and on the right hand side I am going to retain only this term, because this is the term which talks about the radial conduction, okay, of the disturbance variable. So, that is set far away, the radial conduction is important. So, I must retain this, and the idea is this length scale, okay, for large z keeps on increasing, much larger than A times Peclet numbers. So, I am neglecting this also. So, this is also neglected, okay, and that I have to retain. So, what I am going to do is RHS only the radial conduction contributes, okay. And this is the physical argument he made, and then he watch this. So, what I have now is Peclet number multiplied by A by L times 1 minus 2 r squared times d theta A by dz equals 1 by r d by dr of r d theta d by dr, okay. So, what have I done? I just did some averaging, found how the theta A changes, depends only on the deviation variable. Then I found out how the deviation variable is changing, and rather than solve for the deviation variable, I have made some approximation, and I am getting the radial variation of the deviation with respect to the axial variation of the average, okay. Now, the idea is this, this does not depend upon r, because I have averaged out in the r direction. R dependency is only here, and therefore, I can actually integrate this equation with respect to r, okay. I can integrate this with respect to r and get theta d. So, this is independent of r, okay, and we can find theta d as a function of r and d theta A by dz, okay. Now, if you remember that average term that we were talking about, the average term was u dash ud d theta d by dz, okay. This was the average, which this is the quantity which you are interested in, okay. This is what we are trying to figure out. Now, theta d, this is theta d with respect to z, theta d is with respect to r. Theta d, when I solve this equation, I am going to get theta d as a function of d theta A by dz, okay. When I solve this, I get theta d as a function of d theta A by dz. When I substitute it here, I will get second derivative of theta A with respect to z, and that is my conduction, my dispersion term, okay. So, I am just trying to tell you that we have done all of this to do that. I told you earlier we are going to represent this. So, this is what this shows, this term can be represented as d square theta A by dz squared. This term, this term. That is what we wanted to do. So, everything will be in terms of theta a, okay, and then I can go home happy. So, this is the function of r I know, I will get theta d as a function of d theta a by dz, I get second derivative, and so I can write it. You will see how it works. So, let me solve this equation, okay, and to keep life simple, I will right now just take L as a Peclet number, choose. Again, just try to reduce the confusion, okay, in all of you. So, just make this 1 and I can solve this 1 by r, this is just integration. Okay, and integrate this once, what do you get? R times d theta d by dr is r minus 2r cubed d theta d d theta a by dz. What have I done? I have multiplied by r and then I am doing a dr and I am integrating this. Okay. D of this. So, integrate this is r, what do I get? R squared by 2 minus 2 r power 4 by 4 d theta d by dz plus C1, okay, and this on this side will be r times d theta d by dz, d theta by dr, d theta d by dr, okay, and take the r at the bottom and again integrate it one more time. Integrate one more time, I get theta d as r at the bottom, no. So, I get r, right hand side is theta a, thank you, I think you are right, yeah, that is theta a, thank you, yeah. So, I am dividing by r, okay, and integrating it again. So, I get r squared by 4 divide by r, I get r cube, r power 4 by 4, I will get r power 4 by 8, I think. Okay, d theta a by dz, like you say, plus C1 log r plus C2. This is my equation for theta d. Okay. Yeah. So, what are the boundary conditions for theta d? This is a deviation variable. This is going to be bounded at r equal to 0. I do not want the thing to blow up. So, basically C1 has to be 0. Theta d, C1 is 0 because theta d is bounded at r equal to 0. Okay, and I have the no flux condition. So, d theta d by dr, okay, at r equal to 1 is 0. When I differentiate this with respect to r, what do I get? C2 will not contribute, I will get 2r by 4 minus 4 r cube by 8 evaluated at r equal to 1 should be 0. It is automatically 0. Okay. You see that this is r by 2, this is also this is 1 by 2, 1 by 2. So, this is 0. This equal to 0 is satisfied. So, I am not able to find that the second constant C2 using this. Okay. So, what does this mean? I need to get one more condition. I need one more condition to find that C2. One constant was 0 because of bounded, I need to get the second constant. So, now what is the condition I am going to use? I am going to use the condition that the average of theta d is 0 by definition. Okay. So, average of theta d is equal to 0, that is integral theta d 2 pi r dr from 0 to 1 must be equal to 0. So, I know theta d, it is r squared by 4 minus r power 4 by 8 d theta d, no man, d theta a by dz plus C2, this one multiplied by 2 pi r dr must be equal to 0 integral. Okay. So, because the deviations average to 0. So, let us, I mean just integration, I mean we can do it, I mean you can do it better. So, I have r cube by 4, so integral of r cube by 4 minus r power 5 by 8 d theta a by dz plus C2 into r dr. Okay. I have just multiplied by r. Now, I am going to integrate it. I will get r power 4 by 16 minus r power 6 by 48 plus C2 times r squared by 2. Okay. Evaluated from 0 to 1 must be equal to 0. So, I can find C2 using this. Tell me what C2 is. Is 1 by 16 minus 1 by 48 plus C2 by 2 equal to 0. I just put r equal to 1, okay. 2 by 48, 1 by 24, 1 by 12. So, C2 is minus 1 by 12, okay. That is what you should get. So, my point is theta d is going to be given by r squared by 4 minus r power 4 by 8. Hey, what happened? There is a d theta a by dz multiplying this, no? I forgot that. D theta a by dz multiplies these two terms, it does not multiply the third term. So, this is multiplied by d theta a by dz. So, C1 will be not 1 by 12 but minus 1 by 12 multiplied by d theta a by dz. Okay. I forgot this d theta a by dz. So, C2 will be this term multiplied by d theta a by dz. Okay. Yeah. 2 pi is equal to 0, no. So, 2 pi does not matter, 2 pi cannot be 0. So, this has to be 0, 2 pi is just a constant that cannot be 0, therefore, the other things have to be 0. You are right, but yeah. Yeah, now I am happy. This is theta d. Now, just want to take you to that, okay. So, this is the approximation I have made for the deviation variable temperature in terms of the average. That is what I wanted to do, because then my differential equation for theta a will be in terms of theta a. So, go back to that first equation. This is recall, we derived this minus integral from 0 to minus the average. Okay, let me write the average the proper way. When you do average, there will be integral 0 to 1 2 pi r dr at the bottom. Okay. So, this is what we derived right at the beginning of this class. D theta a by dt equals minus of the average of the perturbation of the velocity and the perturbation of the temperature from the average, okay, derivative, etc. Now, if I put theta d, what I can do is I can substitute this expression for theta d here. Okay. I can substitute this expression for theta d here. ud I already know 1 minus 2 r squared. This will be also in terms of r, and this will be d. When I substitute for d theta d by dz, I will get second derivative. The theta d is first derivative of theta a. So, d theta d by dz will be second derivative of theta a, and theta a does not depend upon r. Theta a depends only on z. Okay. So, I can pull it outside the integral, and I only have to evaluate these integrals, and I will get this is equal to something. Okay. So, the RHS is going to be of the form d squared theta d theta a by dz squared. Okay. D squared, because I will write this as d theta a by dz multiplied by the integral, the minus sign, multiplied by integral 0 to 1 minus 2 r squared, and d theta d by dz will be that. So, I have r squared by 4 minus r power 4 by 8 minus 1 by 12 times 2 pi r dr divided by integral 0 to 1 2 pi r dr. Okay. What have I done? I have just substituted for theta d here in this expression. Theta d will give me second derivative, and this remains as it is, this comes here, and 1 minus r square ud 2 pi r dr 2 pi r dr. So, this is some integration you guys can do. I am not going to sit and do it, but I will tell you the answer. Okay. When you integrate all of this, you will get 1 by 48 or minus 1 by 48. Will be this. So, you make sure you get this. The second derivative with respect to z is like a conduction term, okay, but this is really not a conduction. This is coming because of this deviation of the velocity from the average, deviation of the temperature from the average. So, it is not really conduction, it looks like conduction, it is not conduction, and therefore, this is called dispersion. Okay. And it is not a molecular property like conductivity or diffusivity, it is dependent upon the flow. So, what we are doing is, supposing you have some random flow profile, you can write it as a convection term with an average velocity plus an axial dispersion term. Okay. That is how you solve it. Rather than solve for the parabolic velocity profile with actual diffusion coefficient, what we are doing is we are writing it in terms of an average velocity, and then but adding the non-uniformity of the velocity is captured in this diffusion, in this dispersion, sorry. Okay. So, this 1 by 48 is a dispersion. So, 1 by 48 is what is called a dispersion, depends on the flow maldistribution from the uniform average velocity. Okay. So, this is depends upon the flow, not the, it is not a molecular property. This is not a molecular property. Now, last thing I want to do is recall what I told you at the beginning of the class. One term is coming from the conduction term. Okay. The actual conduction term is a squared by L squared d squared theta a by dz squared. Okay. And if I choose, if L is chosen as a times Peclet number, this becomes 1 by Peclet number squared d squared theta a by dz squared. I can't choose it as a, that was the whole argument. Okay. I mean, actually it's more complicated, I am just keeping it simple for today. So, the actual conduction term has a contribution 1 by Peclet number squared, the dispersion term has a contribution of 1 by 48. So, the dispersion term is, so the dispersion term is Peclet number squared by 48 times the diffusion term. Maybe I will write it here. So, the dispersion term effect is Peclet number squared by 48 times the diffusion term, that is the strength, the ratio of one by the other, ratio of dispersion to diffusion. Okay. So, Peclet number is quite large we are looking at. So, basically most of the time what people will do is they will neglect the diffusion effect, they will keep only the dispersion effect. Okay. And now to answer your question which I had the other day, what happens if velocity is high? So, if velocity is high, Peclet number is high. Peclet number is high means the dispersion is high. So, it will spread more. Okay. That is what I am trying to say. So, basically if velocity is high, Peclet number is increases and the spread of theta a is high. Okay. I think this is what you asked me the other day. That is the answer. Okay. So, anyway, I mean, I think you have to sit down and think about it, spend some time, look at the notes, you will hopefully understand this better. But I wanted to do this for several reasons, because the scaling arguments play a very important part in transport phenomena. Okay. It is not that it is very straightforward to do scaling. So, I have told you long back in the beginning that scaling is something you have to do sometimes and redo, redo, and then finally you will figure out the right scaling. at the end of the day we retain only the radial conduction term and another term on the left hand side to do the balance, and we got this expression. Okay. So, this whole exercise is to show that if you do not want to make assumptions, then it does not matter, you can do scaling whichever way you want, because anyway you are not simplifying the equation. But if you are interested in simplifying the equation, which is what we did, you have to choose the right scales. If you do not choose the right scales, you may get some ridiculous results. Okay. And the only way to figure out what the right scales are is by trying out different kinds of scaling. Okay. Okay, thank you.